Good morning, students. So today we will discuss Quantum Mechanics 1, and this is a new syllabus for you, and this is framed by Tansky syllabus of Tamil Nadu. And this is about Quantum Mechanics 1. We are going to discuss the basic formalism today. And of course, quantum mechanics is the main subject, especially in higher physics. Quantum mechanics deals with the small particles. So whenever we talk about the small particles, we always think about the wave function. So wave function for all small particles, this is associated with the wave function. So this was put forth by de Broglie. So de Broglie in the year 1923-24, he said that all small particles are associated or related with the waves. In fact, she took the concept of Albert Einstein's dual character. So Albert Einstein in the year 1905, he said the light particle, the light will consist of dual character. So light will show a particle nature as well as wave nature. So this was put forth by Albert Einstein in 1905. But nature loves symmetry. In fact, in the universe, we have two things. One is radiation, another one is matter. So we have universe. Universe consists of only two things mainly. One is radiation, another one is matter. So Albert Einstein said the radiation has a dual character. De Broglie thought on the other way around, that matter also, because nature loves symmetry, the matter also will consist for two. It has to show dual character. One is a particle nature, and another one is a wave nature. So light has dual character. The matter also will have dual character. So this was put forth by de Broglie, 1923-24. In fact, his thesis was mainly based on nature loves symmetry. So he put forth this idea. Schrödinger in the year 1926, he took this concept, that is concept of all material particles, matter waves, all matter. See, for example, de Broglie says this also will have a wave character. I am also will have a wave character. I have a wave character. Everybody in the universe will have a wave character. Only thing is, this particle will not show prominent wave character. Small particles will show wave character prominently, but this particle will not show. So this was given by de Broglie. So Schrödinger, he took this idea about all matter particles will have wave nature, and he introduced the quantum mechanics, especially in terms of wave function. So mainly his idea was conservation of energy, conservation of momentum. So he framed one equation. That equation is a differential equation, and the solution of differential equation is nothing but a wave function, which we are going to introduce shortly now. So in the basic formalism, we are going to discuss in this unit the interpretation of wave function, time dependent Schrödinger equation, time independent Schrödinger equation, stationary states. So today we are going to discuss interpretation of wave function. Okay, tomorrow we will discuss the next one. And Ehrenfest theorem, linear vector space, linear operator, eigen functions and eigen values, which are very, very important. Hermitian operators, postulates of quantum mechanics, which are the backbone of quantum mechanics, and the simultaneous measurability of observables and general uncertainty relation. So this is for the first unit. Okay. So today we are going to discuss the interpretation of the wave function. Of course, just now we discussed about the wave. So all material particles will have wave nature. Suppose if particle moves, any particle, just take this solid object. This solid object is a classical mechanism. And of course, if I drop this one or if I throw this one, we can easily find out the path of the particle. If I know the initial velocity, I can easily say that whereabouts the particle, where is going to be after some time, what is the height of the particle, what is the final velocity. So everything I will come to know. Suppose if a small particle which is not visible, electron, so small particle, how it is possible to record the path of the particle? So that can be done by means of wave function. So wave function is associated with the moving particle, quantum particle. And this is a state of matter wave as a function of position and time. So any wave function is a function of position and time. So function of position and time. So psi depends on position and time. So any wave function of a quantum particle is associated with the position. We will come to know the position and later the time also. So psi x comma t. So psi r comma t. Psi of r comma t, it represents a 3 dimension. Psi x comma t represents a single dimension. So it moves in a particular direction, x direction. So it can be psi x comma t, psi y comma t, psi z comma t in the z direction. See, all single directions. Psi r comma t represents particle in a 3 dimensions. So particle moves in 3D. So as I said just now, any wave particle which is associated with the wave function psi, which depends on x comma t. And as I said just now, the classical mechanics which deals with the particle, bigger object, will come to know the exact position of the particle. So if I am here, classically I can say that the probability of finding me is 1. Here it is 0. Here I am not here. So the probability of finding myself, here it is 0. This side also it is 0. I can easily come to know. Whereas in quantum mechanics, in quantum particle, we cannot find out the exact position of the particle. We can find out only within the range. So within the range, the particle will be there. So we can say in that way only. So within the range, the particle will be there. That can be easily connected with the probability. So wave function represents the probability amplitude. So any wave function represents the probability amplitude. Suppose if particle is here. Suppose we consider that particle. We will consider this is a quantum particle which is associated with the wave. Okay, any particle which is associated with the wave. Okay, so moving particle. So de Broglie suggested that moving particle is nothing but a wave packet. So this is nothing but a wave packet. Wave packet in which many waves will be interfering. So waves will interfere in a wave packet. Constructively interference where the particle is present. Destructively interference where the particle is absent. Suppose this is destruction, okay, there is no interference at all. So destruction interference. Here constructive interference. So particle is likely to be found more here. Okay, the highest amplitude will give you the exact position of the particle. Which is the highest amplitude? This is the highest amplitude. So particle will be found more at the highest amplitude. Okay, so this is we can say that in the range between this point and that point, the particle will be there. We can say clearly. Okay, but we can't find out exact position of the particle, where it is we can't say, but particle will be there. So this is called probability. But in quantum mechanics, we always concern about probability amplitude. So this is probability amplitude. Okay, so psi always is related with the probability amplitude, which depends on position and time. And look at this wave, it is a positive one and this is a negative one. Okay, so positive axis and negative axis both are there. Negative means it's meaningless. Negative wave function, suppose if I say negative is meaningless. So later in 1927, Max Born introduced this concept. Simply mirroring, we can say that psi is a wave function and it can be a real quantity as well as a complex quantity, and this is negative also. So negative is meaningless. So if you square and taking a modulus, then will give always a real value. So if it is a positive value, negative value, squaring this will give you always a real value. Okay, real value. So that's why Max Born introduced this concept. So this is probability amplitude, this is probability density. So psi is nothing but probability amplitude, but this is squaring of wave function will give you probability density. Probability of finding a particle in a particular range, in a particular volume, is nothing but probability density. For example, you just take, see, I have already told you that we are going to square now. So there is no negative one. So negative wave function is not there. Wave function becomes positive. So now I am going to find out the likely to be found the particle between A and B. Okay, the probability density between A and B is nothing but the area enclosed between A and B. So this is the idea about the wave function. Wave function is the base in quantum mechanics, wave function. So every quantum particle is associated with a wave function, which is a function of position and time. Okay. So for example, as we know already about Newton's law, F equal to ma. So A stands for d squared x by dt squared. So F equal to m into d squared x by dt squared. So if we solve this equation, we will find out the solution for x. Correct? You can find out the position of the particle. If we know the mass, if we know the gravity, we can find out. Similarly, here we are going to introduce a Schrödinger equation. We are going to have the solution. That solution will give you psi. This psi will give you enough information about the quantum particle, where it is, when it will be. Okay, we can find out the range. The range the particle will be there. Okay. So interpretation of wave function or a physical significance of wave function is a very important quantity. Psi is psi. Okay, it's a Greek letter. The wave function which represents the wave motion, wave packet, is called a wave function. Psi is a wave function of a particle in quantum mechanics. So quantum particle are represented in terms of wave function psi. So psi represents the probability amplitude of the system, okay, of the particle. The wave function can be either real or a complex number. Wave function in Schrödinger equation is the observable property. So like in the lab, we always take a measurements. So similarly, the wave function is an observable property. The wave function is a mathematical entity. In fact, Schrödinger himself said that psi is a mathematical entity. All the particles can be represented in terms of mathematics, mathematical quantity. So the wave function is a mathematical entity employed to solve problems in experimental results. So experimental results, we can obtain the same results for theoretically also. So any wave function can be written as a e power ikx. Okay, this is a complex number. Look at this one, and does not depend on t. If it depends on t, we can write a e power iks minus omega t. What is k? K is a wave vector, the direction of the propagation of the wave. So k is the direction of the propagation of the wave. K is a wave vector, which is equal to 2 pi by lambda. Okay, k. Look at this equation. This is a plane wave equation. A e power ikx, a is constant. E power ikx is the plane wave equation. And of course, we know that e power ikx is a combination of sine and cosine. So this wave represents the combination of linear combinations. I'll tell you what is linear combination later. Okay. So combination of sine and cosine. So any small particle, quantum particle, will be represented in terms of wave function. Okay. So psi is called a probability amplitude, as I said, for the position of the particle. Describes the position and the time coordinate. Describes the position coordinate and the time coordinate of the system. Say for example, it is in 3 dimension. Psi of r comma t. Okay, in 3 dimension. If the amplitude of the wave is larger, so if the amplitude of the wave is very larger, the particle is likely to be found more in that region. If it is less, the particle is found to have less chance. So probability amplitude is very important. So psi represents the probability of finding the particle in a particular region. We have already discussed. So we can get all the information about the system. So if we know the position, if we know the energy, momentum, we can get any information about the quantum particle. If you know the energy, especially, we can get from energy we can get wavelength, we can get the velocity, we can get the radius of the quantum system. So we can get it. So we can have all the information about the system if we know psi. So psi can be used to know the probability of finding the particle. The probability can never be negative. So psi can never be negative. Okay. So suppose, as we said, if psi is negative, probability will be negative. Probability can never be negative. Probability will lie always between 0 and 1. So less than 1. So probability can never be negative. So psi will never be negative. Psi will be positive. If we say psi, it has no meaning. If we say psi square, it has a meaning. So we always go with, instead of psi, we always go with the psi square, which is the probability density. So he is Max Born. So he is Schrödinger, as I said, Schrödinger, who introduced this psi in the year 1926, for which he got Nobel Prize 1933. And he is Max Born. Max Born, who introduced psi square, okay, probability density. And of course, he, after 20 years, 1924, he got the Nobel Prize, okay, after a long time. Okay, psi can be used to know the probability of finding the particle. We discussed this one. As I said, psi is, suppose if psi depends on x, a e power ikx, then you can just take the complex conjugate of this. Just take the complex conjugate, it will give you a e power minus ikx. So write I, instead of I, just write minus I. Take the complex conjugate. So psi star is the complex conjugate of psi. So this is the normal wave function. This is the complex conjugate of wave function. So this is the ordinary one, normal wave function. And this is the complex conjugate. If you multiply these two, psi star psi will give you always psi mod psi square. So which is the real quantity and it's a positive quantity. For example, just take psi, which is equal to a plus ib. Psi star, which is equal to a minus ib. So a will become a because it's a real one. This alone will change. So ib becomes minus ib. Multiply these two will give you a plus ib multiplied by a minus ib. Okay. So a becomes a square. ib multiplied by ib minus into plus will give you minus. I into I square will be minus 1. So minus into minus plus. So plus b square. The other term will get cancelled. A multiplied by ib multiplied by a, they will get cancelled. So you will get a square plus b square. So psi will have always real one and it's a positive one. So Max Born, who interpreted psi as psi squared as a probability density of the particle, where you can find the probability of finding the particle in a particular region is nothing but probability density. Okay. So larger value of psi squared implies a strong possibility of presence of particles. Smaller value of psi squared will give you small possibility of its presence. Complex functions associated with the absorption. In fact, from complex function, this complex function is usually connected with the absorption. Emission and absorption probably you would have studied earlier. Okay. So absorption is always connected with the complex function. Thus the probability density is the product of coefficient and its complex conjugate. So this is the coefficient and its complex conjugate. So this is the normal vector, normal wave function and its complex conjugate. Okay. So as I said just now, the wave function is associated with the probability amplitude. Correct? Probability amplitude. So probability amplitude is given by psi dx. It means the probability of finding the particle in a particular region, dx stands for x1 minus x2 or x minus y, something like that. Okay, x1 minus x2. Okay, so that is nothing but p of x dx. In 3 dimensions, this is p of r d tau. So we say this is d tau. Okay, TOU, tau. Tau stands for volume element, which is nothing but dx, dy, dz. So in quantum mechanics, often we will use, instead of volume, we will use only d tau. Okay, often. So p of r d tau, which is nothing but psi star psi d tau. This d tau is nothing but your volume element. Okay. Now we already discussed about the area under the curve, which is proportional, which is probability of finding the particle between A and B. So in the previous graph, we already discussed about this one. So area under the graph will give you probability of finding the particle between the region A and B. So between the region A and B, likely to be found. Okay. Suppose we consider the probability. We are going to find out the probability density of the particle in this graph. We know that particle is somewhere here. We know. Particle is not here. Particle is not here. Particle is somewhere here. We do not know the exact position of the particle. We do not know. Am I correct? We do not know the exact position of the particle. But particle is there between A and B. Okay, so particle is there between A and B, which represents that the answer is 1. 100% of finding the particle in the region A and B is 1. It implies that we are going to integrate. This is triple integration because d tau exists. Triple integration. D tau stands for dx, dy, dz. So triple integration. Probability density. This is probability density. Instead of probability density, you can write psi star psi d tau. Psi star psi will give you mod psi square. Correct. So which is equal to answer is 1. If answer is 1, it means the wave function is normalized, which we are going to see now. Okay, normalized. It implies that the probability of finding the particle between the region A and B is 100%. It implies that this is equal to 1. It means this is 100%. Okay, so this is normalized. The wave function is normalized wave function. Thus the probability density is the probability of finding a particle in a volume element. We discussed any wave function should be physically acceptable wave function. The wave function we discussed just now, wave function psi equal to a e power ikx. As I said, is a combination of sine and cosine. Correct. So all quantum particles are associated with the waves. Correct. These waves should be physically acceptable wave function. So it's very, very important one. If you want to have a wave function, it should be physically acceptable wave function. What are the conditions for physically acceptable wave function? It must be a single value, or a particular position, it should give you a particular value. Another position, another value. Another position, another value. So it must be a single valued function. So any wave function, if you are going to choose the wave function psi, and it should give you a wave function, it must be a single valued function. Okay, first point. Second one, it must be finite. The answer should be there. It must be finite. Finite means mod psi squared integration minus plus infinity d tau must be a real number. The value should be always finite value. Okay, it should be finite value. It must be continuous because we are talking about wave function. So waves will spread. Particles will not spread. Particles are rigid. Waves will spread. So surely it must be continuous. So it must be continuous. Its derivative also is continuous. Okay, its derivative d psi by dx, that also will be continuous. Psi should vanish at the boundaries. Psi should vanish at the boundary means, look at this one. Psi is not here. Correct. Psi is not here. Psi only exists only inside A and B. So it should vanish at the boundaries. Okay. So psi should vanish at the boundaries. That means at x tends to plus or minus infinity, the value of psi will be 0. So these properties are very, very important for any wave function to be acceptable. Okay. For example, we just take psi of x equal to 6 sin x. And of course, 6 sin x is a single valued function. It is finite value. The answer is finite. It is continuous, and its derivative also is continuous. If we are going to differentiate it, that also will be continuous, and it vanishes at the boundaries. At x tends to plus or minus infinity, the wave function will die out. Okay. Suppose we consider this one. Consider this wave function. This is discontinuous. 4 minus mod x. Okay, it's a number. If you are going to give any other value, then it is discontinuous. Okay. So this is discontinuous. It is not continuous. So this is not acceptable wave function. So these are the very important. So this is the physical significance of wave function. Very, very important property. So suppose if we are going to choose the wave function, it has to obey all the 5 properties. So the wave function is normalized. Just now we said about normalization. Okay, normalized. Just now we said normalized. Okay. So this is the condition for the normalization. Correct. So what is the condition? Psi squared d tau equals 1. Suppose the wave function is not normalized. So what will happen? If the wave function is not normalized, then the probability will be greater than 1. If probability is greater than 1, there is no meaningless. Okay, it is not meaningless. There is no meaning at all. If wave function is greater than, if the probability is greater than 1, probability is always less than 1, 0 and 1. We know already. So if it is not normalized, the wave function is normalized, the probability will be always greater than 1, which is not acceptable. So that's why we will have to normalize the wave function. So it means in the particular region, the quantum particle will exist with 100%. This is the idea about the normalization. Okay, the wave function will exist, surely it will exist in the particular region. This is answer is 1, but we do not know where it is. We know the range of the position between A and B. We know the range. Suppose the wave function is not normalized, for example, then you have to multiply with a suitable normalization constants. So these are all normalization constants, which are very important. Normalization constant. You have to multiply the wave function with a suitable normalization constant. So A stands for normalization constant. A psi star, A psi d tau equals 1. So you pull A out, so that will give you mod A square psi star psi d tau, which is equal to 1. So mod A squared will be 1 divided by integration minus into plus infinity psi star psi d tau. So one can find out the normalization constant easily using equation 1.6. Okay, so this is about the normalization. So normalization, just now we have some ideas about normalization. Now we will go for orthogonal. Suppose a wave function satisfies both normalization and orthogonal, we say that this is orthonormal wave function. So you have wave function which is normalized. If you have the wave function which is orthogonal means perpendicular. Okay, we are going to see now what is orthogonal. The answer will be 0. Suppose if you have two wave functions, psi 1 and psi 2, two wave functions. Psi 1 and psi 2, okay, we have two wave functions, psi 1 and psi 1. Psi 1 star, psi 1 will give you answer 1. Psi 1, psi 2 will give you answer 0. They are linearly independent wave functions. We will see what is linearly independent. So they are all orthogonal. Orthogonal will give you result 0. Normalization will give you result 1. So put together, we say that this is orthonormal wave functions. Okay, is it clear? The heading is clear. Suppose if we consider the wave functions for quantum particles, psi 1 of x, psi 2 of x, psi 3 of x, represents many particles. Then just take the complex conjugates. Take the complex conjugate. Psi 1 star of x, psi 2 star of x, psi 3 star of x. Okay. Now we are going to just take the product. We are going to take the inner product. Inner product is nothing but like taking a dot product. So we know already about dot product earlier in mathematical physics. We studied about, in vectors we studied about dot products. Okay, I dot I, j dot j, k dot k will give you 1. I dot j will be 0. So in vector space we already discussed earlier. Now just take the inner product. So this is inner product. Now just take the inner product. Okay. So psi 1 star psi 1, psi 1 star psi 1 will give you answer 1. Okay. Suppose if I take psi 2 star psi 2, answer will be 1. Psi 3 star psi 3, answer 1. If I take like this, psi 1 star with psi 2 or psi 2 star with psi 1, answer will be 0. So this is the condition for normalization. This is the condition for orthogonal. If any wave function satisfies both normalization and orthogonal, will give you orthonormal wave function. So this is the general idea. If the first condition is satisfied, then we can say that they are normalized. Second condition is satisfied, then we can say this is orthogonal. Put together, this is orthonormal wave function. So any doubt on the slides? Okay. So generally put together. So we have written separately. We are going to write put together. Together we can write this as psi n of x, psi m star of x, dx equal to del nm. If n equals m, will give you this. Correct? If n is not equal to m, will give you the second condition. Correct? So one is 0, another one is 1. So we have 1 and 0 if n equals m. if n is not equal to m, the answer is 0. This is called Kronecker delta function. So we discussed earlier in mathematical physics already. Okay. So psi n of x, psi m star of x. Suppose if n equal to m, generally we can write this as psi n mod psi n square dx. This is known as square integrable function. Very important concept in quantum mechanics. It must be square integrable function. So any wave function must be square integrable function. What is the meaning of square integrable function? We are going to square, see, square and integrate. So square integrable function. Now we will go for a small idea to find out the amplitude, that is the normalization constant. Just take psi, the total psi, which represents the quantum system, consists of all small particles. Okay, we'll just consider a system consists of small particles. So each particle is represented in terms of basis. So they are all bases. For example, we know that